This week. So we did a little weathering because we kind of need to understand that for some of the sedimentary rocks. I'm going to cruise through this. There's a lot of info here. I'm going to try and leave a lot of the rock stuff for the lab. And so what we're going to do is talk about the two different groups we said. In weathering, we talked a little bit about that we have these rocks that are sedimentary that are made of pieces, and there's a certain process for identifying that. And then there's rocks that are chemical or biological, and there's a different process. But the idea of clastic sedimentary rocks is that we break down pre-existing rocks, we transport those, we deposit those somewhere, and as more material gets deposited, they become compacted. And actually what happens is, over time, fluids will move through these open spaces. We call these pore spaces. And as the water moves through here, it's got a lot of calcite sometimes, or silica dissolved in the water, which can precipitate out as little crystals. And those crystals will grow in the pore spaces and become the cement that holds the pieces together. And so we need this compaction and cementation process to occur. It's occurring as the material is being buried, and then we can hold the rocks together. So what we want to do is look at the different pieces and make some evaluations about them, and that can help us figure out the environment of deposition, which is the ultimate goal, and tell us something about where maybe these things came from, right? So we take the sediment, we turn it into sedimentary rock. One of the things that we want to do is to look at the sediment pieces themselves, and the first thing that we do is look at the size of the pieces. And so we actually use the terms sand and mud as a size determination. So when we look at a rock, we want to say, can I see the pieces with my naked eye? Kind of like sand at the beach. These would be sand-sized particles. If they're bigger than that, then we're going to call them gravel. Now, it doesn't mean that every piece in the rock is bigger than 2 millimeters. If any pieces are bigger, you're going to put it in the gravel category. If any pieces are bigger than the mud size, we're going to put it in the sand category. So yeah, there's silts and clays, but for this class, we're just going to call them muds. The good news is when we start to name some of these rocks, sand-sized pieces make a sandstone. Mud-sized pieces make a mudstone. So not too bad for some of those things. But size isn't the only thing that helps us name the rocks. So we want to look at how big the pieces are. The biggest piece in the rock is going to put it in these categories, either gravel, sand, or mud. Then we also want to look at the shape of the pieces, because that tells us something. In general, we're going to argue that the rounder the pieces are, the farther they have traveled, because they bounced and rolled and the edges have become smooth. So we would say they're either angular clasts or pieces or rounded pieces. So we want to be able to make that observation when we look at classic sedimentary rocks. We want to look at sorting. What does sorting mean? It means that are the pieces all relatively the same size, or are they just a mix from big to small? If they're not all the same size or big, small, everything, we would say they're poorly sorted. If they're all about the same size, we would say well sorted. So different environments do that. And so if we can make these observations, we're honing in on the environment where these pieces formed, and that can tell us the story that we read from our sedimentary rocks. What else we got? So also, what are the pieces made of? So they're either kind of heterogeneous, where they're all over the board, they're made of everything, or they're homogeneous, where they're all the same. Once again, I can tell you where these pieces came from. So if this is a volcanic rock and this is something else and something else, that's the source area. Those things were weathered and eroded from somewhere else, and I might be able to tell you where that came from if I know what they are. And so knowing the composition of the pieces can help us with the story. And so as a general rule, we would argue that the farther from the source you are, the smaller the pieces will be. Now, does that mean that here, close to the source, that there are no small pieces here? No, it means that you will have big pieces that you won't have way out here. So you'll have a variety of pieces and sizes, big and small. They should be very angular because they haven't traveled very far. And they should be poorly sorted because they haven't traveled very far. As I move away from my source area, the pieces get more rounded, a little smaller. They're still kind of poorly sorted in this sample, but they're not as poorly sorted, let's say, as that. And then, of course, I move farther away and farther away. And really, what I'm showing you here are the four main clastic sedimentary rocks that we see. Sandstones, made almost entirely of sand-sized particles. Mudstones, made of mud-sized particles. These two are similar when we describe them in that they're both poorly sorted and have gravel-sized pieces, but the rounded clasts in this sample tell me it's different from here. So rounding of pieces almost always means water transportation. And so the big pieces tell me a river that had some velocity. Down here I could still be in the river, but the velocity is probably not as great because the pieces are smaller. So remember, distance from source can do things for size. They're smaller. We're also going to say that size gives us another indication, and that is of energy. How much energy it takes to move or deposit. It takes a lot more energy to move this size piece than this size piece. So if I see very small mud-sized pieces and I'm trying to figure out what environment might I see mudstones in, I'm not going to think of a raging river. Because a raging river would pick up big pieces, number one, and number two, it would never deposit these because the energy is too high. In order to get these really small pieces to settle out of the water, you need the water to have either no velocity or super low so the muds can settle out. And so I'm looking for a low energy environment, not really close to the source for something like this. As I get farther up where the pieces are bigger, higher energy environments. So we can use those things to help us understand the depositional environment of these different samples. Okay, so this is kind of what I just went through in that previous diagram, and it's just this idea that, right, distance smaller, but also energy is related to the size of the pieces, and so we want to take that in consideration when we're figuring things out. We said here's the rocks that we were talking about, right? Conglomerate or breccia, the only difference is the conglomerate has rounded clasts, the breccia has angular clasts. And then sandstones and mudstones. Boom! You know your clastic sedimentary rocks. You observe the pieces and make the call, right? So that's the clastic story. So just some images, right? So, and you'll see these in labs. We got that going on. We got sandstones, and there's a variety of sandstones. I'm not going to get into the different types for this class. Just kind of more concerned that you can identify a sandstone, even though there are other names we can give them. And then siltstones, shales, mudstones, we're going to kind of interchange those terminologies for this class anyway. And so we've got, those are the small pieces. Now look, we also have the rocks we said that are not made of pieces. We're going to lump them into the group called chemical or biochemical. And so how do we identify those? Because for clastic, we just looked at the pieces. Here we look at what is it made of. And so real quick, I'm just going to run through some of these rocks, and we're going to see this in lab. But limestones are made of calcium carbonate. If I can identify a rock that's made of calcium carbonate, I know it's limestone, because that's how I'm going to do chemical rocks. In geology and in the field, said we use a little acid, and we drop a little acid onto the rock sample, and it bubbles and fizzes. That's a reaction that I get from the mineral calcite, which is CaCO3, which forms the rock limestone. So they both would fizz, and that tells me that I have a carbonate or a limestone of some kind. So I also have rocks that are made of SiO2, pure quartz, and there's a bazillion names for the different kinds. But usually when we talk about sed rocks, the rock name we give to bedded silica deposits is called a chert. We use properties to identify those. Chert is made of quartz. Quartz is very hard, so I can't scratch it with a nail. So in the field, I can't see pieces. I try to scratch it with my steel knife. It doesn't scratch. I know it's quartz. I name it a chert because I identified what it's made of. evaporites, so we can get gypsums and halites. So salt deposits, if you're not sure what it is, if you're in the field and geologist and nobody's looking, you take a lick, oh, it licks, tastes like salt, it's halite. But they're also softer. Gypsum's very soft. I can scratch it with my fingernail. So we're still identifying what it's made of to give it a name. Coal, usually you can see, it's kind of this shiny, it's dark like this. In theory, it's a little softer, and of course, I guess I could lay it on fire. That's the test. But made of carbon, I'm identifying what it's made of to give me the name. Okay, so the second part of all of this is to figure out where these rocks were formed, and so they can be on the land, or they can be in the ocean, or somewhere kind of in the middle there, in what's called a transitional. Oops, let me go back for a minute, sorry. So continent, transitional, or marine. And so the whole goal of looking at rocks is, in igneous rocks, we looked at them and you could tell me, hey, that came from a volcano. How did you know that? You looked at the small crystals and said, oh, that had to make it to the surface. You looked at the color and could tell me its composition and figure out what makes that on the surface of the earth, and kind of tell me where it was created. Oh, it has big crystals. That had to be inside the earth, and there had to be an uplift event, and there had to be erosion and weathering that stripped off all this stuff, exposed it. That's the story you can tell with igneous rocks. I want to do the same with sedimentary rocks. We pick them up. It's made of pieces. Okay, how big are they? What's the shape of them? What are they made of? And then we think, wow, these really big pieces mean high energy. It's not going to be a lake where it's super quiet, or a floodplain where it's just kind of muddy water just hanging out. This is going to be near a mountain front, or maybe a raging river or something like that. Or this is sand particles, a sandstone. Maybe that's a beach environment. Maybe that's a desert environment. Limestone, almost always water. Majority are formed in the oceans. So think of like Bahamas and things like that. That's where limestones form. So this is what we want you to be able to do. We have a couple extra clues to help you with that. So besides just looking at the size or composition, a lot of sedimentary rocks hold structures. Structures that are preserved in the rock, and they formed when the rock was being formed, and they tell us a little more information about the environment of deposition. So just because this video is getting a little long, I'm going to make one more about that, and we'll be good.